Welcome to Easy Math TV. This is the second part of our video discussion of a continuous uniform distribution. Last time we solved problems involving calculating probabilities using the graph that you see here. But so if you want to understand rectangles and areas of rectangles, go and watch the previous video. Today, though, we're going to complete a grouped frequency data table that would represent a continuous uniform distribution. So I'm hoping that it will help to clarify some maybe last minute confusion or maybe some just some points that you might not have been 100% clear about. So again, we have our population is on the x values from 0 to 5. So we have a continuous uniform distribution on the interval from 0 to 5. And that's all we need to know, is that it's continuous, it's uniform, and the interval is 0 to 5. That information tells us everything we need to know. Okay, so the way I decided to do it is we have our total interval has a length of 5, and it's pretty easy to split it up into intervals that have a width of 1/2. So basically, just our bin width is going to be 1/2 or 0.5, and that's going to result in 10 bins of values of x. 10 bins of values of x. Okay, which is a nice round number to have. So you can see the 10 bins right here in column A. This is how we're splitting up our values of x. The minimum value starts at 0, so the first bin has a left endpoint of 0, and the last bin has a right endpoint of 5. So you'll notice that I actually had to include that value there. All right. That last interval has a square bracket on the right. Every other interval does not have a square bracket on the right because we do not want them to overlap at all. Okay, so first you want to set up your x's in column A. So let's just set up our x's in column A. Square bracket 0, comma 0.5, and then you put a curved bracket or a parenthesis to the right of that. So 0 to 0.5. The second bin is square bracket 0.5, comma 1, and then put a curved bracket to the right. So each of these has a bin width of 0.5. And just keep typing those in all the way down until you get to the last value of x that we can even allow. Okay? And notice we're not going to create another bin that has square bracket 5, comma 5.5 because these need to be the same size, and each bin has to have a width of 5, and each bin has to have values of x that are allowed. Okay, values of x that are possible. So because of the fact that this is a continuous distribution, so we wouldn't be doing this if it was discrete, but the fact that it's continuous means that this last bin is actually going to end at the rightmost value of our interval, which is x equals 5. Okay, so that's the only exception between discrete and continuous random variables, is that because it's continuous, we're going to have that last bin end at the rightmost endpoint, the maximum value. All right. So I want you to, I guess we don't need to worry about column B here. What I did this just for graphing purposes. So if you wanted to graph this, you would list all of the endpoints here under column B. I didn't, I only did that for graphing. So you don't need to have that, but that is an optional column. And the endpoints are just basically the very first number that you see in each bin, okay? The very first number that you see in each bin. And then you do that all the way down to 4.5, but then you also go one more row and end it at 5. Okay. That, and again, that would be just be for graphing purposes. And so if you asked Excel to graph this, it would start at x equals 0 and it would end at x equals 5, and it would not go past that point. We do need this number though in column C. So how the heck did we calculate 0.2? Where does that number come from? So that is step 1 in our probability calculations, or creating our probability data table. And so little f of x is what we call the probability density function. This is not giving us the actual probabilities for these numbers. So that's what causes some confusion, okay? Little f of x is just the height, that's measuring the height of rectangles that we need to calculate the area of. And then, so then the actual probabilities are going to go in column D. Okay? It's going to go in column D. So little f of x is just a number that's going to be, it's a multiplier. It's going to get multiplied by something. Okay? But we do need that number. So it's called a probability density function. And on the uniform distribution, little f of x is a constant. And you can see it's just 0.2 all the way down. So we calculate its value using the range of x. So basically you can just assume that this is just a formula that applies to any uniform distribution. Little f of x is equal to 1 divided by the range of your capital X. In this example, the range is the maximum minus the minimum. So 5 minus 0 equals 5. That is our range. Therefore, little f of x is equal to 1 divided by 5, which is 0.2. So you literally just type in the 0.2 and you can just fill it all the way down, like so. And so if we were to graph it, we would just highlight columns B and C, and you could create a scatter plot of that. But we're not going to do that. Column D. This is where we calculate our probabilities. So I want you to think of little x. Our bins are basically the values of x that we're calculating probabilities of. Okay? They can't be individual values of x. We talked about that before. When it comes to a continuous random variable, you can't split things up into just individual values of x. X has to be split into intervals. So each of these intervals has a width of 0.5, right? So the probability of each bin is equal to the bin width times little f of x. So I'm going to type equals here, and we're going to take the bin width, which is 0.5, and we're going to multiply that by the number that you see in C3. So equals 0.5 times C3, hit enter, and then fill down. So these probabilities have to add up to 1. Those are the probabilities that have to add up to 1, because you are covering, this is all values of x, right? Are you convinced that any value of x between 0 and 5 is included in one of these intervals, and these intervals do not overlap at all? So the total of all of the probabilities has to equal 1. So if you take, there are 10 of these, so 10 times 0.1 is 1. Okay? So that hopefully clears up some of the confusion. Little f of x is not measuring the actual probability for each of these intervals. It's telling you what you need to multiply by. Okay? These are the actual probabilities. Okay, so let's calculate a couple of probabilities and using this table. And we are limited, so the only downside of using the binned data like this and a grouped frequency, it's actually not a grouped frequency data table, it's a grouped probability data table. So I should probably go over here and change that to probability data table. We can only calculate probabilities on intervals that begin or end at one of the values that you see here. So, for example, we wouldn't be able to do 1.75 because 1.75 is not one of these endpoints. But we can calculate the probability that x is less than 1.5 because 1.5 is one of the endpoints. So you can see that I'm going to just put x's next to the ones that are included. So these are the 3 bins that have x less than 1.5, right? And so to calculate that probability, you just add up these 3 numbers that you see in column D. So the probability of x less than 1.5 is equal to 0.1 plus 0.1 plus 0.1, which is 0.3. So you can actually use a grouped probability data table for continuous data to estimate probabilities of outcomes. You can do that. It's totally fine. Let's do one more. What is the probability that x is greater than, x is greater than 3? Okay, probability that x is greater than 3. So you have to ask yourself which intervals of x would that be? And I'm just going to kind of highlight them down here quickly. So starting with 3 and going all the way up to 5, right? So 3.01 or 3.1 we want to count. So 3.1 is in the bin here, all the way up to 5, right? So I'm counting this, this, and this. Those 4 bins cover all x's greater than 3. So how many 0.1s do we have? We have 4 of them. So 4 times 0.1 is equal to 0.4. Okay? Let's do just one more. How about 1 is less than x is less than 3.5. So x is between 1 and 3.5. So basically, go to the first bin, the bin that starts at 1, that's here, and go up to 3.5. So, and right? Those are the bins that start at x equals 1 and go all the way up to 3.5. So count the number of x's that we have. There's 1, 2, 3, 4, 5 of those. So 5 times 0.1 would be 0.5. So the answer to that probability question would be 0.5. Like, subscribe, comment down below if there's any additional questions you have about the continuous uniform distribution. I can try to answer them for you. But that pretty much covers all of what we really need to know about it, because then we're going to move on to the most famous continuous random variable of all, which is the normal distribution. All right? And I'll see you in the next video.